Yeah, I'm sharing my screen. Yes. So this assignment is visible.
Yes, it's visible.
Yeah. So in in assignment two, what we have to do, we have to just so the motto behind giving this kind of mathematical expression was to just exploit the coalescing, and you have to minimize the thread divergence. And so by to what is the meaning of exploiting the coalescing is that you have to use the concept of shared memory. If you will use that, then it will be the coalesced access. So, if you will see, there are two operations that actually we are using on this matrix X. The final output is X, and we are using four matrices A, B, C, and D. So we are adding two matrices A plus B. Can anyone tell that do we need shared memory for the addition of matrices? Can you all hear me? So my question is, can we require this addition for addition A transpose plus B transpose? Do we need any kind of shared memory, or it is fine that it will work without shared memory? Or okay, I guess there is no answer. Yeah, there is some answer, I guess. Actually, I'm not able to see the Google. Yeah, so Binong is saying there is no need. Why there is no need? Okay, let me explain that. Okay, somebody has explained. No, no reuse. Okay. So, when we are performing this addition operation A transpose plus B transpose, then there is no need of the shared memory because we are accessing the memory in the contiguous fashion itself. And when we are accessing the memory in the contiguous fashion, it means our access is coalesced access. So, like in the last class, you might have seen that a group of 32 threads is called as warp. And if you will try to access these contiguous location of 32 threads in one go, then the speed of GPU is going to be fast, right? So if you want to access it in coalesced fashion, then this is the best way that you can do. Otherwise, it will become more strided access to the memory. So when we perform this addition operation over the matrices, like we have A matrix and B matrix, and suppose we did the transpose of A matrix and the transpose of B matrix, and when we add it, then we add it element by element, and we pick a particular row or column, however we are doing. Just assume that we are doing the row measure manner, and when we do this, we will add it by element, and we are doing it in a contiguous fashion by picking a one chunk of the memory which are highly coalesced. So that's why we do not require this shared memory. But when we do the this matrix multiplication, there we have lack of coalescing, and then we have to see a way to make it more coalesced, so that uh, like uh, we can just use the we can use this in the coalesced fashion. Also, uh, like uh, we can use this efficiency of GPU. Like otherwise, there will be a waste of GPU writing. If you are writing some kind of program on GPU, and if it is not more optimized than memory has, then it will require more memory cycles to bring the things from the CPU. Then it is a waste. So we have to think upon. So like I will just give you the concept that like how we have to this do this C transport D. So A transpose plus B transpose is fine because it's already coalesced. Now we have to perform, after getting this result, we have to multiply it with C transpose into D. So this is not a vector thing. We have to do matrix multiplication thing. So we have to multiply C transpose into D, and for that, what we have to do, I am just on Jamboard. Sorry, there is a answer. A plus B whole transpose. Oh, is it? No, I didn't get it. A plus B whole transpose. What does that mean?
Sorry, I have instead of doing A transpose plus B transpose, I have distributed the work to CPU and GPU and computed A plus B and then transposed the matrix.
I see. I see. Okay, I will look it into that. Okay, so okay, where I was? Okay, so okay, this is Jamboard. Okay, so like just give a fair amount of idea that how actually we have to use this multiplication thing and transpose thing. So first, just assume that this is a so assume that this is the thing, and so what we are doing, we are taking the things in the chunk. So chunk means this is one chunk, this is another chunk. So since a WAF consists of 32 threads, so we can take that idea and we can define our like when we do this problem, we can define that okay, the since WAF consists of 32 threads and that are in the contiguous fashion and that can be brought in one go. So it will be fast, right? So it will be more coalesced and it will be fast. So why not give the size to 32 itself while defining the block size, right? So at that time, you have to think about that while you are writing the program. So I guess you might have done like that, but I have not seen your answers. But this is the idea. Like in the last class, you might have uh, read about these things. So like we want this chunk right at one go, and this side similarly at the one go. So what we are doing is just so assume that this is a matrix, some input matrix, and just assume that we are doing transpose first, not multiplication. And now what we have to do in transpose, what happens? In transpose, we just interchange the rows and columns. Yes, there is message.
Sir,
Yeah, actually, I'm not able to see this.
sir, can you hear me?
Yeah, please.
Sir, I have taken the block size 16 because I think it is more like it's not. I think it is experimentally like what I want to say is that the dimensions are here only 2 power 10, right? 2 power 10 plus 2 power 10. I thought it would be better if we take 2 power 5. I think the most of the test cases, I thought the block size will be more like. So I have taken a smaller block size, like taking
And
it as
that is fine. Okay, I was just telling you that how we have to exploit it.
okay, sir. I was just asking. Okay,
Yeah, fine.
thanks.
So now what? So what is the like? How we have to do the problem is that. So suppose this is a input matrix A, and now we have to transpose it using some shared memory concept, using the coalescing concept. Now what we have to do is that we have to put this in some shared memory, and then we have to copy it to back to the output matrix. So this is our input matrix, and our expected result will be what? It will be a some matrix A transpose and A transpose. This is our output. This is our input, and this is our output. And what we have to do is that so this chunk will be in the form of what? Will be in the form of this, right? So this we want. So from this input, we want this one. So so how we can do that? So I already discussed that if we have some kind of assume that this is a how we are accessing it. Suppose this is now assume that this is a thread. So these are the threads: thread one, thread two, thread three, and thread four. So if these are the threads and these are accessing the contiguous element of this array, so like this thread is accessing this element, this thread is accessing this element, and so on. So this is like we are accessing the contiguous elements of this array, and if so what will happen that a warp will try to bring it, and it will try to perform the operations, and and it will become a coalesced access, and it will become more fast as compared to strided. In strided, what will happen? Like a thread will have like that, and again it will try to do like that. In a similar manner, it will try to do. So it will become less efficient as compared to this. Like I told why, because uh, a warp consists of 32 threads, and it is going to be brought in one go. So now what we have to do? Now in between, we have to take the concept of shared memory. So we have to use shared memory concept SM. Okay. So we have to use the concept of shared memory, and let me. So we have to use the concept of shared memory. In that, what we have to do? We have to just copy this. We have to copy this to shared memory. And now, after copying this to shared memory, we have to do some kind of transpose to it, and assume that we did the transpose here itself, uh, in the shared memory itself. And after doing the transpose at the shared memory, now we have to copy back it to the output. So this is clear to all. This is fine because this is how we have to do the things. Is this fine? Okay. So the thing is that we have to use the shared memory concept here. So for that you need to use sync thread also, because we are trying to uh, do it like in a so sync thread will be barrier to a block, and like if we are performing the operations, so in that suppose we have just taken the elements from a particular block, and after doing that computation to a particular block, all the threads in the particular block has computed it, and after that certain operations has to be done, then we can put it as a we can put a sync thread so that all the operations are done. It will act like a barrier, right? So if so what is the meaning of barrier is that if all the operations are done before that point, and we want to wait to other, if some threads are fast and if some threads are slow, so we will tell that okay, you have to wait for that thread to finish it the execution, and then we will meet at once at barrier. So they all meet at barrier, and later they start executing the later part of the things which are below the barrier, right? So this is how sync threads work as a barrier for the shared memory. So this is the concept. Yeah. So
Hello, sir.
yeah.
Sir, assuming that I have, suppose I have implemented all the thread algebra and I have converted 2D into 1D, and let us say take the block size as 5.
Okay.
So it will be 25 threads, and I think in that case we don't need any sync threads, right? And I'm assuming that the block I'm launching a 1D block, but although I'll do the thread algebra and get the corresponding indices, like we are using the tile, right? We may need two indices, and suppose I have launched a block of size 25, block in the sense uh, sorry, this block size, and the tile size is 5, and now the tile is 5 cross 5, and the number of threads working on it would be 25, and that is less than 32. So in that case I think we don't need any sync threads, right?
Um, yeah, because if that number is less than 32, I guess uh, then it is going to be coalesced fashion. But uh, I have to see the range of like constant, and I will get back to you like uh, what I have to do. Like I have to see your like solution, and
No sir, I have implemented with block size 16, and I have used sync threads, but I'm asking uh, whether it is true that whatever I told it is right.
mm, I guess if we are using no the way how we are launching the kernel will also depend, right? So
Yes sir.
assume that we are launching the kernel with a huge number of threads, right? So okay, let me show you the one of the way that I have used for launching the kernel. So uh, so you can see that. Okay, it's not here. Uh, yeah. So you can see that we are launching it like for transpose. Uh, we are doing dim 3 32, 32, right? So we are taking it as a maximum. We are not also,
Yes sir, so continue your discussion that you have launched dim3 32 comma 32, right?
yeah,
So we can also launch it as serially, that is 32 into 32 1024, and make it and visualize it in the kernel as 2D. We can do that, right? So we can convert 2D into 1D. So if I do that, and with instead of 32, I'll take 5. Then it will be 25 threads. So in that case, I don't think we require the sync threads, because by here we are using sync threads so that the array is copied to the tile, right? Comfortably, the array is copied to the tile, but the tile
yeah,
itself size is 25.
yeah, yeah,
So I think we should not worry whether because the warp itself runs in a lock fashion, so the
yeah,
tile
yeah.
will be successfully copied.
Yes, yes.
Okay, sir.
So it is if it is less than 32, then there is no problem. But I guess the constants are high and we need it. Okay, so Soumik is saying that add matrices is launched on PQ, but Q can be much higher than 1024, right? If Q is much higher than 1024, right, you need to make it in the form of blocks, right? So Q you can fix it at 1024, and because that is the highest number it can have, and then you can divide it by 1024, that like size to make it in the form of number of blocks. So now what will happen that it will get you will get some different number of blocks having different sizes like 1024, 1024, and in the last block might contain less number of threads than 1024. So In that manner, it will get scattered. Is it fine, Swami? Okay. So this Jade is asking, why are we, but Q is less than 1024. Okay. Okay, that is fine, right? That is like how we so this is how we have to do it. Like what I told to Somik is that like in the worst case, like even if it is a even if the constants are very less, right? So we should not worry about if the constants are less. Just assume in the worst case that the constants are big, then how we have to do the things. This is how we have to do. That's what I told to him. So like Jade is asking, why are we using shared memory? There is no reuse while transpose as well. Okay, so like Shojit, like can you tell me that what is the meaning of memory coalescing? If you know the memory coalescing meaning, then you will understand that why we are using the shared memory. Even if like if we are not using the shared memory, things will work, but the performance will degrade. Now you have to see that how you can improve your performance. So to improve the performance, we have to use some kind of so like first of all, why we are using tiling? That is very important. Tiling we are using because we have to improve the performance. Otherwise, we can do simple matrix, this multiplication thing, and we can do it without using the concept of shared memory. But I think Rupesh has taught you in the class that how we have to uh, do the matrix multiplication uh, on GPUs, right? How we have to do. So simple way you could have done it, like how it is taught in the class. But why we are using tiling is that we want some kind of improvement, like so to get some kind of improvement, we want that okay, we want the size of that tile to be this, and we want to make the computation full for complete whole tile, right? So if you are doing that, it means that you need not to recompute the things and go to the memory again and again and bring back. So the whole tile block will get into the you will take it in one cycle, and you will do the performance. You will do the operations whatever we have to do on that. Is it fine, Jed? Do you have any more doubt on that? That your question was why we are using shared memory. Is it fine? That what I told you? I guess. Okay, let's move to. Okay, okay. Thank you. So Pirapuraj is asking what cudaMalloc was working without SM, but it was not working in SM in collab. Uh, this thing I cannot tell you because I don't have the knowledge of this collab, Google collab thing much because generally I works on GPUs on my system or some server that we have. So don't have much knowledge of working on collab. Why the cudaMalloc was not working? Do anybody has experienced the similar kind of problem and can help Mirapuras? Like he's asking that cudaMalloc was working without SM, but it was not working in SM in the collab. Like I don't have any answer to this. If anybody knows, can can you tell it? Because I guess I have like one or two times used Google Colab. Otherwise, I have not used it, so I don't have much experience using Google Colab.
Yeah, one point here is yeah, people have used both shared memory and cudaMalloc earlier on Google Colab. So unlikely that the problem is while using shared memory. But in case you continue to face problem, Pirapuraj, please feel free to share the code with us. We'll be able to debug it.
Okay, sir. Okay. I'll share. But it was working in first assignment. But so I was trying yesterday with shared memory. But I so if I remove that, it is working. But it was not working. That's why I
Yeah, my
asked.
guess is there might be some other issue which we might want to check. Unlikely that it is related to Google Colab. Mm, just send it across. We'll be able to take it.
Okay. Okay.
Sure.
Yeah. Okay. So also, so any more questions? Okay. So I'm not discussing the solution right away because there are some people like who has some problems like installation problems because I got mails about the installations, or like there are some people who are not able to do it due to the limit over the Google Colab. That also I got. So like it, so like you can submit the things like uh, it was that it was intended to submit it before 12 o'clock, but there are some problems, so you can submit it. You can take your some more time, I guess. Rupees, can they take some more time?
Yeah, maybe the participants can take time for today, but that will also mean that their time for the next assignment might reduce. So just be aware of that. We are permitting late submissions because many of you are starting afresh, but try to be as much on time as possible.
Yeah. Yeah. So for that, we have to like uh, diminish this discussion of this assignment. We will discuss it later. Okay. Can you ask? Yeah, please.
Yes, sir. So you have mail regarding. I have mail regarding this CUDA-Free, right? So suppose we are suppose a kernel is working on a matrix and the matrix is in use, and next after the kernel invocation there is a CUDA-Free of the array which is used by the kernel. So I have a doubt whether without uh, computation getting finished, the array will be freed because I'm not sure whether this will be queued into the same queue, or if you take the cudaMalloc, the memory is allocated and the CPU is blocked until the memory is allocated, right? So I'm worrying whether this will free and will block the CPU until it is freed.
No, how we are using it that matters, right? So assume that we have a problem statement in which, like I already told you over this email,
Yes,
right?
sir. But I did not.
Okay, I will tell you that. So what happens is that assume that there are some array that is being used in a loop, right? And in that loop, it will be get updated in a contiguous fashion, right? It will be so for I equal to 0, the things are updated, and for I equal to 1, again it will work on the same set of data. So in that case, if you are writing the CUDA free inside the loop, so it is going to erase your previous data, right? So how it will work for the next iteration? So it is useless. So generally, what happens is that generally we used to put the CUDA free things after we are finished with all the computations, just to remove the extra spaces or memories that are being used. So
Sir, yes, sir. That scenario is fine, but my scenario. I'm trying to say a different scenario where there is no loop. Like we want to, yeah. So I don't want to print anything. So after computation got finished, I want to just free the memory. But is it guaranteed that the computation is finished and then after the free memory is freed, or irrespective of whether the kernel is executing or not, the memory is freed. Consider there is no loop or something like this. Only kernel call and kernel invocation, and then this free, CUDA-free.
Yeah, so even if you will, even if you will not put this CUDA free, right? Even if you are doing some computation without a loop, or simply you are doing like a plus b or any kind of computation you are doing. So even if you will not put this CUDA free, it is not going to hurt you, right? But the good practice is that you just put it at the end of the program, so that nothing is left in the memory, right? So that you do not how we do the free thing in the like C, right? So in that manner we have to do the CUDA free in the CUDA programming. So uh, I'm not sure whether the automatic garbage collection, like what you were asking in the email, right? Something like that, that automatically it will happen or not. So uh, I'm not very sure. Rupesh, does it happen automatically? I'm not very sure.
Yeah, so there is no garbage collection happening on the GPU as of today. But this question of whether if I do CUDA free from the CPU and kernel is executing, uh, whether CUDA free will uh, is it getting queued or will it cause any issue with the existing kernel? I'm not sure. My guess is that it should create some problem. I'm not sure if it gets queued up. Maybe it gets queued up, but I'm not sure. Yeah, so that part I'm not sure. But yeah, to safeguard against this, it's best to do uh, uh, CUDA device synchronize. And yeah, so there is a suggestion from Soumik that CUDA free is synchronous in nature actually, so it will wait for kernel to complete, I think. No, so this synchronous asynchronous part is with respect to the CPU. So there is a CUDA free async also. But what that means is that the CPU will wait for the CUDA free to finish and CUDA free async for it to not finish. So, but with respect to the GPU, it doesn't, at least to the extent I know, the documentation doesn't say anything. But in case you have found it out, please share with me. I'll be happy to know.
Yeah, so my time is over, and I guess no more questions. So now Rupesh can take it over.
Sure. Thanks, Shovik. Thanks, sorry, Ashwin. Let me stop the recording.